Okay, so you're given the logits 1.5, -2, 3. So your computer has done a linear combination of all the features and come up with 1.5, -2, 3 for the 3 classes, class 1, class 2, class 3. And you have to convert that into a probability. What is the right formula? And people said 11 people are in this one with an e to the -2. 4 people are in this one with a 1+. And the 1+1 is very tempting, but wrong. So if you chose the 1+1, you got it wrong. The reason this 1+1 comes up is in the one-dimensional regression, you only have one number. You have, is it a binary classification, class A or not class A? Then we use like a formula like this. And this formula has a 1+ because we're sort of thinking of there's 2 classes. There's actually class A and not class A, but we always put in a 0 as the other class. So this 1 in the formula is actually an e to the 0, and we're always sort of in the one class case putting in a second class artificially, which has a 0. And so watch out for that 1. If you chose the 1 there, that's not right. So most people got it right. So let's kind of review how this stuff works. And we have, we can pick up where we left off last class over here. So the formula is and this is the softmax function for probabilities in the softmax function. So the probability of class I is e to the logit I, let's call it logit sub I, and then you divide by the sum of e to all the other logits, including I again. J equals 1 to the number of classes. And so the thing I just said is watch out in one let's say like one class logistic regression, we insert a 0, logit equal to 0. So in one class regression, it's e to the x divided by e to the 0 plus e to the x. So that's like if you have x0 as your number, it turns into the e to the x over e to the 0 plus e to the x. And so we've artificially inserted this 0 to make it 2 classes, the class and not the class. In a multi-class problem, we really have some number of classes, right? So we have logit 1, logit 2, and ... logit n. There is no reason to insert a 0. Okay. All right, that's one nice thing. Here is the other fact that I talked about very briefly last class. Here is the fact that I used last class, or I said it out loud, is that if you start off with some logits, logit 1 all the way up to logit n, and you compute the probabilities, so you do softmax of this vector, which gives you the new vector of probabilities, that is exactly the same thing as doing the softmax of the logits with a constant added. So if you do logit 1 to logit n plus c, and you add the same plus c onto every single vector, it is exactly the same thing. So that is to say, as an example, if someone says we got 1.5, what was the example that I gave? -2. So the number's -2, 3. 1.5, -2, 3. If those were the logits, or if the logits came out to be, I don't know, let's subtract, let's make c equal, -3. C equal -3. And then you would have -1.5, -5, and 0. So the logits could come out like this, the logits could come out like that, and the claim is the probabilities will be the same either way. Softmax. Okay, and why is that true? That's because every single term over here will get a plus c. So when you go to compute the probabilities, you add a plus c in every exponent. And if you add a plus c in every exponent, that is the same thing as multiplying by e to the power c. E to the power c. And if you multiply the top of a fraction and the bottom of the fraction by e to the power c, those cancel out, and it's like you did nothing at all. So adding c in the logits, because everything is exponentiated and then is then divided, completely cancels out, and it doesn't do anything. And the reason this is useful, you'll see when we go back to our computer programs, that we don't want to have big numbers in our logits. Big numbers can potentially cause the computer to get angry at us and explode, and so we always subtract off the biggest number so that the maximum number is 0. So here the maximum number was 3, and by subtracting 3, I made it so the maximum number was 0, and it doesn't change anything, but it just makes the computer kind of more stable. Yeah, and there's sort of an asymmetry in the computer, right? If you put an e to the big number, then it gets mad at you and explodes. So the e to the big number, the computer will say, not a number, this is terrible, I'm so mad at you, and nothing is going to work. But if you put an e to the negative big number, so you put in like a super negative number, then the computer's like, oh, I know how to handle that, that's just 0. So the computer can handle really big negative numbers, but not really big positive numbers, and that's why we subtract off the biggest positive number to make things 0. Okay, I'll show you that in a second. All right, any questions or comments about the math so far? Okay, so now that we remember this part, let's go back to our notebook that we were working with. And today I'm starting with the notebook example called MNIST with second half blank. Let's see if I can make it appear. MNIST with second half blank, and that's because we did the first half last class. And so the first half is all filled in, but the second half is blank. All right, and what is it? It doesn't like something. What does it not like? It doesn't like my layers. My output size should be 10. Okay, great. I think we did that last time. Oh, okay, great. Okay, actually, let me recap what we have so far before we go any further. So last class, what did we do? We started playing with these Lego bricks, and we took the MNIST data set, which was these digits, and they are 28 by 28 pixels, which adds up to 784, a vector of size 784 with all the pixels. And we first did something totally weird on it. We did linear regression, and that was this picture over here. So we started out with linear regression, which was just this. We had the inputs of size 784, and we did a linear combination, that formula, to get the output. And then we said, that's the thing we're trying to make close to the label of the digit. But that turned out to be kind of silly, because it could be less than 0, and it could be bigger than 9. And so we were getting things like, oh, it predicts this is a negative number. It predicts this number is 100, which doesn't make any sense. And so we added on this non-linear layer, which was taking all the numbers and smooshing them down to 0 to 9. And that was what I called non-linear regression. Let's see if that's here. So here was our function. And then we did the regular thing, and it was doing some silly stuff, like it was saying this one was negative 12. And then we did non-linear regression. In the nonlinear regression, all we did is we took the output and we added this function to it. Let's zoom in a bit. So we did the sigmoid function. The sigmoid function smooshes the numbers to be between 0 and 1. And then we did 9 times it to make it between 0 and 9. And then we trained that, and that was a lot better. So we were training this thing, and we got a loss of like 3 point something. So if our mean squared error is like 3 point something, that means we're on average off by like 1 or 2. So if the real number is like 4, we're guessing it's like 6 or something. And so here are some examples where we were pretty close. Here, yeah, this one says 1, and we guessed 1.95, so we were sort of off by 1. Here, this one says 9, and we guessed 7.76, so we're sort of off by almost 1.5. That's what we did last class. And all of this was trained, by the way. The other detail that is important that we did is we trained it with gradient descent. So here was the picture of the gradient descent. We calculated the mean squared error, and then we were always just changing the parameters to make the mean squared error a little bit smaller. And we were crossing our fingers and hoping that it works. And there was all sorts of issues with like, where do you start? If your starting point is not in a good spot, it'll be hard to find the minimum. If your step size is too big, like that green error, it'll be hard to find the minimum. So you have to tune things a little bit. But when it works very well. You minimize the mean squared error, and that is how we were doing. So all of that is stuff from last class. Any questions or comments about what we did last class? So today we're going to do more of it. It's going to get gradually more complicated until we end up with something really good. Okay, let's see how it goes. So the thing we're starting this class that we started off last class, at the very end, is logistic regression. And the big difference is that you should recognize that what we were doing over here is kind of crazy in that we were predicting a number, we were treating it as a regression problem, when really it should be a classification problem. If the real answer is 4, and you say 5, you might as well have said it's 9. In fact, 9 and 4 look kind of similar as digits. So I'm kind of more sympathetic to somebody who writes a 4 that looks like a 9 than someone who writes a 4 that looks like a 5. So how far off you are in numbers is kind of meaningless. You should either get it right or not. So we shouldn't do regression, we should do classification. And for classification, that's where these logits come in. So we have a logit for each class. There's 10 classes, and therefore we have 10 outputs. And what we have just discussed is this softmax function, which converts the logits into probabilities by doing this. And that is exactly where we left off last class. So let's do that one more time. And the very last thing I think we did is I was doing this formula for the log of the probabilities. And it's just a fact of nature that we're not going to need the probabilities themselves. We're only ever going to use the log of the probabilities. You might think that's a little funny, but for example, one thing we have to do is find the maximum. If you find the maximum probability or find the maximum log probability, it's exactly the same. And so the log probabilities are nice to do. And you got to be able to do the log of this formula. When you do the log of this formula, the e to the x, the log of e to the x just becomes xi, and this denominator becomes a minus sign, and you end up with the log of the sum of the exponentials. Log sum x. And that was the very last thing we put in our code. So let's do that in our code now. So logistic regression, the first thing you got to do, the first important change, now the output is size 10, so the network outputs 10 outputs instead of just one output. And then our function, the logistic regression underscore log p, which returns the log parameters, the formula for the log p is you take the logits and you subtract off the log sum x of the logits. And the other trick, which I also mentioned, is we're not going to use the logits themselves. We're going to use logits max 0, which is the logits where we've subtracted off a simple thing. And that avoids the computer exploding. OK. Max 0 minus this. OK, and that should work. OK. So this should work. Then what else have I done? I've done the same exact trick as before, which is using JAX.vmap. So instead of doing one example at a time, by v-mapping it, vector mapping it, now I can feed in all the examples at once and do it that way. So hopefully this will work. OK, let's see. So here is logistic log gr on one example. So these are the log probabilities for one single image. And here it is on all the examples by using that vmap formula. You see the first one is the same. There's 10 numbers here that tell you the probability. It's the log probability that it's a 0, the log probability it's a 1, a 2, a 3, and so on. The 10 different classes it could be. OK, that's what we have so far. Questions or comments? It really is taking things we've done earlier in the course, but now we're writing them sort of in a very hands-on way. Earlier in the course, we didn't worry too much about the details. We let scikit-learn do it for us. Now we have to do it ourselves, because when you do it yourselves, you can make more complicated things. All right, the next thing we need to do is we need to do the error function. So we're going to train it with gradient descent. It's going to be the same thing as before, but we're going to measure how well we're doing. That's going to be a little bit different, because now it's not just one number. Before it was compare this number to that number. Now we have 10 numbers, right? We got these 10 probabilities. How do you compare these 10 probabilities to the true answer and figure out how much error there is? That's the thing you got to minimize. So you got to tell the computer, please minimize this. And the formula is not the mean squared error anymore, because now it depends on 10 vectors, or a vector of size 10. And this is, again, something we did earlier in the course, but let's see if you remember in, if I can find the right tab, mathematize, probabilities to loss function. So you are working on a classification problem. For a particular example, your algorithm thinks the probabilities for class 1, class 2, and class 3 are 0.2, 0.3, and 0.5. In our problem, of course, it's a 10-class problem. This is an example with a 3-class problem. If the true label is class 2, so this is actually the digit 2, then what should the loss be? And I gave you some examples of what it could be. Hit none of the above if it's none of these. So how do you go? In other words, how do you convert from the probabilities to the loss? How do you convert from the probabilities to the loss? And I'll let you think for a minute. You might need to open up your notes from earlier. This is the cross-entropy loss that we did when we did logistic regression. Okay, time is almost up. If you're not sure, I guess take a guess as which one is the right one. How do you compute the loss when you know the probabilities and the true class? This is the cross-entropy loss. Okay, what did people say? Drum roll. All right, so nobody fell for this. This one is like, if you were in mean squared error land, this is what you would do. But we're not doing the mean squared error. Right? This is like the distance between 0.2, 0.3, and 0.5 to the vector 0, 1, 0. So this is like mean squared error land. If we were doing a regression task, then that would be the kind of thing we would do. How far away are you from the real answer 0, 1, 0? It would be this. But that's not what we're doing because it's a classification task. And so the answer is going to involve logs. So let's see. Out of 18 people, about half the people are in this one, and about half the people are in not this one. So I think what we need is a little refresher on how this thing works. Let me remind you of the cross-entropy loss and how we derived it. And then I'll have you guys revote, and we'll see what the answer is. So if you remember, the way this works is the mean squared error loss, that was the log likelihood for a Gaussian. So a Gaussian has a probability of e to the minus x minus mu squared. There's some other stuff, but don't worry about that. And so we thought it was x. The real answer was mu. That was the log. That's the likelihood. And the log likelihood is the log of this, which is minus x minus mu squared. And I guess everything is negative the log likelihood. I always forget the negative. Okay. So plus x minus mu squared, that was the mean squared error, and that's where it came from. So if the real answer is mu, and you guess x, you get a penalty of x minus mu squared. That's how we did the mean squared error loss. What was the cross-entropy loss? The cross-entropy loss. This was negative the log likelihood. Again, likelihood. But not for a Gaussian, for a Bernoulli. A Bernoulli. And so what you have to do is you have to write down if the real probability is p, and we guess that it's p hat, what is the chance we see that? And yeah, okay, it's p hat to the power 1 with probability p. And it's p hat to the power 0 with probability 1 minus p. This is the likelihood. And we want to minus the log of that. Okay. And so this leads us to the formula. When you take the log, it's either 1 or 0, you end up with this formula, p times the log of p hat plus 1 minus p, sorry, it's 1 minus p hat to the power of 0. Okay, log of 1 minus p hat. So this was the formula that we derived before from this kind of consideration. So this was what we had before. And again, this is very slightly different than what we have now because this is the two-class case, right, where there was just one p and one p hat. How does it generalize to the multi-class case? And in this situation, we're not seeing a p, we're seeing an observation. So you can kind of think of it as p is either 1 or 0. Okay, but that's a little refresher on what we did a few weeks ago. Maybe you also have your notes, or the course website has some notes. But that's the kind of thing that we're doing. And so now I'm going to give you a chance to revote. Feel free to chat with your neighbor. Try to remember how this stuff works. And let's see if we can get a majority of people in one answer or another. And remember, just because most people voted for this one doesn't mean it's the right one. Okay, let me open this up again. I'm going to repeat the exercise, and then we will see how we do. Okay. It's open, and I got to hit this button to bring it back. Okay, here it is. Version 2 is open. What is the right answer in this situation? Okay. Okay, let me give 1 minute. Okay, 10 seconds. Put in your final guesses, and we'll see how people did this time. Okay. Let's see what people did. Let's turn the beeping timer off first. Okay. Reveal counts out of 21 people. Now 19 people are in minus the log of 0.3. And that is the right answer. So very good job. Another way you can sort of do it directly, we think the likelihood of class 2 under our predictions is 0.3. So what is the negative log likelihood of what actually happened? It's negative the log of 0.3, right? And so the idea is you want to make this 0.3, if it really is class 2, you want to make that 0.3 as large as possible. Like if you made it 0.99, then you would get minus the log of 0.99. That's like almost nothing, because the log of 0.99 is very close to 0. So the sort of the lower the probability you put on the thing that actually happens, the more you get hit on the head for making a mistake. You want to put high probabilities on what actually happens and low probabilities on what doesn't happen. So that's the right answer. Now we have to take this idea and put it into our code. So let's do that. And is this the right one? This is not the right one. Where's the Google Docs version of this is the one I want. Yes, here we go. Here's the copy of the code that we'll save as we go. Okay, so we did this. Okay, now I'm going to put in the the cross-entropy loss. So the CE loss for the log(R) function, the logistic regression function, the first thing I do, I get the predictions. The predictions, remember, are actually log probabilities. Maybe that's worth writing in a code. Preds is the log probabilities of all the classes. So we take in the whole set of images, and the target is the actual labels. We first computed the predictions using our function. That was the function we wrote before. It depends on the parameters, and it inputs the images. And this is where, to calculate the cross-entropy efficiently, we need to take our target. Our target is a number, like 2 or 3 or 4, depending on what is the output. And the predictions are vectors, right? This is the important thing. The predictions are vectors. It's a vector of size 10 for each image. The target is a single number. And so to make these two things gel together, I'm going to take the target, which is a single number, and convert it into a vector as well. So that's target as a vector. And this is called a one-hot encoding, which we've seen before. And the command to do this, I believe, is .1hot. Yeah. So you want to do 1 hot of target, and you have to say I'm going to make it a vector of size 10. So this converts numbers to vectors. Let's do an example. Like you could convert 4 would get converted into the thing that has 0 in its fourth thing. 0, 1, 2, 3, 4. So it'd be like this. So if the true answer is 4, this one-hot function will make it into a vector that has a 1 in the fourth component. Remember, we started 0. So 0, 1, 2, 3, 4. That's the next vector. And we're going to use that to calculate the log probability. The one-hot function is part of the JAX family of functions. It's JAX.NN. So that stands for JAX.neural network. And so this is a function that will do this very efficiently. It'll convert the number of the target into a one-hot vector. Okay, so now we have this vector of one-hots. Is this vector of one-hots making sense? You guys did something similar on your projects. Okay, so next up we got to do the cross-entropy loss. And the cross-entropy loss, the formula is going to be this thing we had before. It's the P times the log P prediction P, and it's summed up over all the classes. So sum over all classes. This is what we just talked about. In this situation, the vector P, those are like the true things that happen. That is exactly target as a vector. So if we do target as vector, and then the log predictions, those are already done for us. Those are the preds. Those already have the log baked in. So we sort of saved ourselves some time by leaving it as a log. The preds is already the logs. And to sum over all the classes, we use the jnp.sum function. jnp.sum. Okay. So this will totally work. One thing that's a little bit annoying is this will give you the total of the cross-entropy loss total over all the examples, because remember, everything is actually doing it over all the images. And so if you want to get the average cross-entropy loss, like the average mean squared loss, you do jnp.mean. And so that'll be exactly the same, but it'll average it as you go. So that's the formula. So this remember, times is the entry-wise multiplication, and that's really what we want here. We multiply this size 10 vector by this size 10 vector, and when you multiply by this size 10 vector, it multiplies them all by 0, except for the single 1. And that is exactly like, imagine we were doing it in our example over here from Mathematize, right? We have the vector 0, 1, 0, and we would multiply the logs of these numbers by 0, 1, 0. That would give us exactly the answer we want, the log of 0.3. So this one-hot vector is exactly sort of like pulling out the log of the probability of the real class and leaving all the other ones and deleting them. Okay, so let's put it back. That's not it. Here it is, okay. So that's all perfectly correct, except for I made one small mistake. Minus, yes, okay. So same mistake as always. When you're doing gradient descent, if you have a minus sign, it will make your model worse and worse every time instead of better and better. And it's important there's a minus here because in the cross-entropy loss, there's a minus. But that's the right formula. And now if I run it, it should also give me the cross-entropy loss. what is the cross-entry loss on all the examples? 2.78, it says. You can sort of calculate, there's 10 classes. Let's do a little envelope math here to figure out what the cross-entry loss means. I've lost my pen. So can someone see the pen? Okay, here we go. So let's pretend that our model is really unsure and outputs a 10th for every single entry. So like when you start your model, it's like, I have no idea if this is a digit 0 or digit 1 or digit 2. So it's like, I'm just going to predict 10% chance of all the digits. Okay. So this is our prediction p hat. What will be the cross-entry loss for always predicting a 10th? Let's calculate what it would be. Well, you know what? It's going to be one of the digits. Maybe the real digit was digit 1, and you're going to get a 10th. And then so your score will be minus the log of 1/10, also known as the log of 10. And we're doing everything log base e here, because that's the natural log. So if you predict a 10th, a 10th, a 10th, a 10th, no matter which digit is chosen, your cross-entropy loss will be always log 10. What is the log of 10 these days? Log 10. Oh yes, we need the AI to tell us what is the log of 10. Okay, 2.3. 2.3. So if we were perfectly predicting a 10th, a 10th, a 10th, then our cross-entropy loss would be 2.3. What is our actual cross-entropy loss? It's a little bit worse than that, 2.78. Why is it a little bit worse? Well, the model is not actually doing a 10th, a 10th, a 10th. It's doing random numbers. Some of them will be a little bit higher than a 10th. Some will be a little lower than a 10th. We can look at these predictions over here because I made the computer print them out. So if these were all equal, they would be all equal to negative log of a 10th, which would be, they'd be all log of 1/10, which is negative this. Okay. So they should all be negative 2.3, but they're not negative 2.3. Some of them are like negative 1.5, negative 3.6. So because some of them are a little smaller and a little bit bigger, then we're making worse than average errors, but not much worse. So everything kind of gels together. This is about what we expect, and everything is making sense. Questions or comments so far? We're about to try to train it. So yeah.
I'm getting like minus 32.
If you're getting minus 32, then it could be that your initialization is not close to all zeros. So if you get a 10th, a 10th, a 10th, then you're getting like negative 2.3. Where did these 10th, 10th, 10ths come from? They came from doing the softmax on stuff that's all approximately equal. So if you have 0, 0, 0 as your logits, then when you convert to probabilities, it'll be a 10th, a 10th, a 10th. If you have some numbers that are much bigger than the other numbers, then you won't get a 10th, a 10th, a 10th. You'll get like one number that's much bigger than the other ones. So when you initialize the network, you want to make sure that these numbers are close to 0. And if they're not close to 0, you'll have a very spread out thing. I don't know if you remember last class, I drew this picture of the sigmoid. And I said if you start over here on the sigmoid, then you get very bad results. And that's like starting with large logits. So you want to start your logits near 0. This is better. So that it has a chance to learn. And you want to start over here. So I would try to change the initialization. I'm not sure why yours came out different than mine. Maybe you changed something about the initialization, but let's see. Where did I initialize things? So here the parameters got initialized, and they got initialized with the default size, which somehow is right to do it. But okay, so for me, it's working at least. This is a great question. Anyone else? All right, here's the beautiful thing. We don't actually have to do anything else. Like you can take this thing, you say, please minimize the cross-entropy loss, and it fits into the exact same function as we did before. There is one bonus thing you can do if you want. So everything will work. And there's one bonus thing you can do, which is you can ask it, please do the accuracy. Before we couldn't do the accuracy because it was a regression model, but now we can say, please tell me which class has the highest probability. The highest probability. And that's the predicted class. So to do the predicted class, you do an argmax. So the maximum will give you the maximum value, and the argmax will tell you which class has the highest value. So I'm going to do the argmax of the batched predictions. Batched, log-gr, log-p's, parameters. And I want to do axis equals 1, so the computer was right. So the batch log p's is an array. It's 10 by 10,000. So for all of the 10,000 images, it has the 10 log p's. I want to take the largest value in that dimension with the 10, and that's axis equals 1. So this will return a big vector with equal to the size of the number of images, and it will tell you what we predicted. And our accuracy is how often the predicted class is the target class, averaged over all the predictions. So this little mean here tells you how often were you correct. This is called the top 1 accuracy. Sometimes people do things like the top 3 accuracy, like how often is the real answer in the top 3, and so on. But that's the accuracy. And I can feed the accuracy function into our training loop. It doesn't change anything. All the training is based on the cross-entropy loss, but it tells me how accurate things are as we go. And that is useful to know. So any questions or comments while this thing is running? So it should be running. It's minimizing the cross-entropy loss. So it's doing this little dance. Let's draw the picture again. We'll draw a copy of this picture. So once again, we have the parameters. The parameters are 10 times bigger than before. The parameters, this time it's 10 by 784. So for every pixel, there's 10 parameters now. But once again, you can think of it as minimizing the cross-entropy loss, which looks like this. And we start somewhere at random, and we take little gradient steps to go down to the bottom of the hill. That is gradient descent. Okay, and it's running. And here we go. So after one run through, our training accuracy was 84%. Our test accuracy was only 83%. And remember, we started with cross-entropy loss of 2.7. Now the cross-entropy loss is 2.3, which is, again, not great. A training loss of 2.3 and a test loss of 2.7 is saying we're basically guessing all of them are equally likely. That was after going through our data the first time. But after going through our data again, look, we're doing way better. Right? Our training accuracy is 0.87. We're 87% right. And our test accuracy is also 87%. So we're getting most of these right. And our loss has gone down to 1.3. What does 1.3 mean? Well, let's take e to the 1.3. That'll undo it. We did a negative 1.3, so we've got to do a negative. 30%. So we're saying this basically says of the 10 classes, the class that is the real actual class we think has a 30% chance of happening, basically. So this is better than 10%, like we've gone up from 10%, but it's still not great. Why don't we keep training it? Let's keep training it for a little bit. So all I got to do to keep training it is comment out the lines where we start the parameters from the beginning, and I'll just say keep training, and it should get better. So let's see if we can improve that 80%, 87% accuracy and 1.3 as our cross-entropy loss. Let's see if we can improve it a bit. Okay, here we go. It's 1.2 now. So 88% and 1.2. Okay, and here we go. It seems to be settling down. It is not improving anymore. It's kind of flattened out. It's not improving much. Let's see what it looks like. We can ask the computer to output some predictions. That's over here. And it will show us some pictures. So this is a thing, and we think it's a 0. Hey, that's great. This is a thing. We think it's a 4. Very wonderful. This one is a 1, and this one is a 9. So all these 4 examples we have done perfectly. And in fact, we're doing 87% of the whole data set we've done perfectly. So we've gotten it right 87% of the time. With these 4 examples, they are perfectly correct. Yay, we did it. This is a logistic regression. Any questions or comments about how it works? So the thing we're going to do now, I think we've basically done all the hard work. The thing we're going to do now, it's going to take us like 5 minutes or something. It's not hard to do it all. We're just going to add in a couple more things, and it's going to be almost no work. We've done all the hard parts, and it's going to take our accuracy from like 87% to like 95%. And you might think that's only a 7% improvement. But it's really like a 2x improvement, because this is like a 13% error, and we're going to go down to like a 5% error. And all we have to do is make the model a little bit more complicated. And this is the beautiful thing about what we've done so far, is it works no matter how complicated this picture is. So this is the picture that we drew. This is what we're doing right now. This is logistic regression. But now that we know how to do these things, you can make the model as complicated as you want. You can add layers. You can add weird functions. You can do all sorts of stuff. And it's no extra work. So as long as you can draw a picture like this, you can make it work. And so what I'm going to do very simply, I'm going to take what we had before. This is logistic regression is this before, where these were the inputs. These were the inputs. And then we did one layer into the logits. These were the logits. There was 10 logits. There were 784 inputs. And then we did the softmax function, softmax, to get the predictions. These were the log p's, or 10 of those. So this is everything we've done so far. And I'm just going to do the exact same thing, and I'm just going to add some more layers over here. So I'm going to make this not the inputs. Let's use our little lasso tool and grab the inputs. The inputs are going to go all the way over here. I'm just going to add more layers, more layers. So the inputs are actually going to start over here, and I'm going to add these things called hidden layers. These things are called hidden layers. And when you add hidden layers, you add lots more parameters. So before, we had, how many parameters did we have? We had parameters just from this. We had 784 by 10 parameters that were connecting this layer to this layer. That was what we had before. But now I can add more parameters on each of these layers. So there'll be more parameters here and here. It is your choice how big these hidden layers are. Let's call them H1 and H2. They can be as big or as small as you want. And we're going to add parameters. There's going to be, I guess this one has to be 784 by H1. This one has to be H1 by H2. This one is H2 by H3. And this thing becomes H3 by 10. So we're, instead of doing the input directly to the logits, now we have these hidden layers. And this lets us include many more parameters, and we hope that that will improve the model. Some people say this is increasing the capacity of the model. The number of pieces of information that the model can memorize and use now has increased. Right? Before it was just this, and now we've added on all these other ones. So let's see how this works. Okay, so this is a true, what people call a multi-layer perceptron. This is like the most basic type of actual neural network, and it's called a deep neural network because it has many layers. And actually, the very important thing is the cross-entropy loss part. That was the hard part, and we did all that already. So almost all neural networks, even the most complicated ones, even the most, like ChatGPT ends with this. This is like how every single neural network in the world works. They always have this last layer at the end if they're doing classification. So this is the hard part. We've done all that. This part is super easy. Well, I'll show you how it works. So all you got to do is in our layer sizes, before it said 784, 10, right? Now you just got to add in a couple more things in here. And so you can put in H1, H2, H3, and you can make those whatever you want, and it'll work out. Let's start with, let's make these some things. Let's do an H1 and H2. Let's make them like 500 and 200. I don't know. I'm just making up stuff. And let's not do an H2. Let's just do an H1 and H2. And so this will tell the computer, please make all the layers, make all those parameters. And remember, we had a list of all the parameters. Now the computer has successfully knows to make all these parameters. Okay, so that'll work. So this init network params inputs this list and makes all the parameters for us. And then you just have to tell it what to do in this loop, right? This was this is the function. Before, we were doing only the dot product. So we did JNP dot, and we did W, X plus B. That is 1x. And then this loop will loop over all the hidden layers. So all you have to do is do it again. So please just do JNP dot of WX plus B, and please do it again. In the final layer, we're going to do it again. So JNP dot final W, X plus B. So this does the first layer. This loop is looping over all the layers and doing it again. And this final layer is when we go to the logits. Then we do the logits max 0, just like we did before. And the log p's are exactly what we saw before. They are the logits max 0 minus the log sum x of the logits max 0. So this part is exactly the same as the last layer before. This part is the same as the beginning. And now we're just looping and doing it again and again and again. So it's really just taking the computation and feeding it one layer at a time and looping through and doing it. And you just tell the computer you can do anything you want here. Like you put any formula you want, do any like weirdo stuff. It's all fine. The computer will know what to do as long as you describe it sort of with this kind of code. So you have a vector and you have it work. Okay, it doesn't like B. I guess this should be final B. Final B. Okay. Is that my problem? Okay, now it works. And so here I applied it to one example, and I got -3, -2. These are the numbers that are all approximately -2.3, approximately 1/10. Questions or comments about what we're doing? Yeah.
The hidden layers, what exactly is going on there? Is that the pixels are just getting compressed in 500 and 200? Or
Yes, this is a great. So I think what you should think of is before we took the inputs, which were numbers, and we turned them into the logits. Now we're turning the inputs, which are numbers, into other numbers, and we turn the other numbers into other numbers, and we turn the other numbers into other numbers, and then we finally do the logits. But every single thing is a linear combination of the previous layer. So like there's some parameters here. There's like a W1, 1, 1, and this is W1, 1, 2, and this is W1, 1, 3, and so on. And the value of each hidden layer is just a linear combination of all these weights with the previous layer. So we're just taking the single math operation that we're doing always, is what we started with last class, is this operation. Right? We're just taking this operation and doing it over and over and over again. I don't know why I left that x1 out there. But this is the only operation we're doing. This is the J and P dot of W and X plus B. And so every layer is J and P dot W of X plus B of the previous layer. And you just stack it and do it over and over again. So we're doing this operation like 3 times instead of just doing it once, with different W's and B's for each layer. Does that answer the question? It's a great thing to understand conceptually. And that's why I started with like wanting you to understand this very well. The whole network is just this, repeated over and over again. Okay. Any other questions? Yeah.
Sir, there is input layer.
Yes.
Different hidden layers.
Yes.
And one output layer.
That's right.
So per layer, how much one bias is only there?
What's the deal with the biases?
Yeah. So
This is a great point. So there's I should say there is a plus B, plus B, plus B. So each layer has its own bias. Right, in my picture. Okay, this is B0, B1, B2, B3. So in each layer you have these matrices, and then you do this linear combination of all the W1s with the X's, and then you add on a B. So each layer comes with a bias, and that's a vector that just gets added on. Each layer has its own bias.
But like
yeah.
In the neural network of like the video you have like in the playlist, so they were saying that there are 235,000 parameters in 784 pixel problem. So they were calculating 256 biases per layer.
Yeah, right. So of course, I just made up the H1, the H2, and the H3. If you set them to the right values and you make the right number of them, you can change the number of parameters. In my picture, the number of parameters is 784 times H1 plus the number of parameters in this B, which I guess is H1. Then there's H1 times H2 plus the number of parameters in this B, which is another H2, plus H2 times H3 plus another H3, plus H3 times 10 plus another 10. And if you add that up, you get some number. I don't know. I just made them up. So if you do it a different way with different H's and different number of layers, you're going to get a different number of parameters. We could calculate what it is if you want. The thing is, the number of parameters is sometimes not very helpful. Sometimes you add more parameters and not much changes. So the number of parameters in a neural network is not always indicative of what's going on. If you just like add them in willy-nilly, it won't change anything. Actually, why don't we train the network, and we'll see what happens, and then I'll have more to say about this. Okay, so we do it. Let's train it. Okay, so here first we batch it. So the VMAP takes our function and batches it, and then cross-entropy loss is exactly the same as before. And now we run it. Okay. Oh, this is okay, so now it's training it. Here I put in 784, 784 times 10. So I only have one hidden layer, and the hidden layer size 784. But you could do the other one if you want. The computer will do it no matter what you do. This will speed things up a little bit. Okay, so 0.85. And the training loss is 0.0679. Ooh, that's very small. The accuracy is still like 85%. Why is the... Okay, so we ran it. The thing I want you to notice, after 2 runs through our data, the training and the test accuracy is very similar to what it was before. The loss function is reporting that it's a lot smaller. I don't know why it's doing that, but let's keep training it and see if we can get to the 95% or whatever that I was saying that you can get to. So let's keep training it. The mean.
Why there are 784?
Okay, yeah. So I made the network have one hidden. This network only has one hidden layer of size 784. So it's like the one in this picture has 3 hidden layers. The one I'm actually running only has 1, and its hidden layer size is 784. The more hidden layers you have, the slower it will go. So if you're at home and you're waiting, then it's fine. But if you're running it in class and you want it to run relatively fast and only take like 20 seconds per run, then only one hidden layer is fine. Okay, so here's what I want you to notice. The training accuracy and the test accuracy is not much better than it was before. So before I was like, oh, if you add more layers, it'll do better. But it's not doing better. It's doing actually exactly the same as what we had before. It's doing exactly the same as logistic regression. And that's because in this picture, it's very nice. I added more parameters, and I did these linear combinations, the J and P dot every time. But unfortunately, I forgot to do something that's very important. And if you forget to do it, then you will not actually do any better. So what I was doing before was only one layer, and now I have many layers, but it's actually the same exact function. And the reason is I made every single function linear. So if you write this as matrix multiplication, what did I do? I said take the weights of W1 and multiply them by the weights of W2 and multiply them by the weights of W3 and multiply that by the input. Oh, I suppose it's the other way around. Like this. 1, 2, 3. So, okay, there's plus b's, but forget about the plus b's for now. So this is what I'm saying. The output is do a linear combination of the inputs, and then do a linear combination of those, and then do a linear combination of those. And here's the thing about linear operations. Instead of doing W1 times X and then W2 times that, you could have done this all in one shot. You could have just done W3 times W2 times W1 times X input. And what this is saying is if you have a 3-layer network and 3 matrices, they combine down to make one big matrix by matrix multiplication, and you might as well just do a 1-layer network. So this is what this is saying, this little math that we've done, is saying that a 3-layer linear network, it's exactly the same as a 1-layer linear network. And you've just like made it more complicated. So like this thing, the final dimensions are 784 by 10. This thing is like 784 by H1, and this one is H2 by H1, and this one is 10 by H2, right? And like when you multiply them all out, all these dimensions like shrink down, but you get the final same dimensions. There's no point in making a 3-layer linear network. You might as well just make a 1-layer linear network. So adding more layers, in terms of matrix multiplication, you're not changing the space of possible things you could do. These things are exactly the same set of functions. They're both linear functions. So adding more layers seems like it's not doing anything. There is one secret thing you can do that makes it's like completely magical and completely life-changing. You'll get a completely different set of things. And that is to add in nonlinearities. So we saw that earlier, that another thing you can always do in these networks is you can put in a nonlinearity anywhere you want. And so a 3-layer linear network is exactly the same as a 1-layer linear network, but a 3-layer nonlinear network is completely different. And so this is the last little secret ingredient that we need. And it took researchers a long time to realize that what you got to do is this. We're going to add in a nonlinearity. So we're going to add in a nonlinearity And this is what it's going to do is just going to transform each individual output here by applying a little nonlinear function to each of them. And it can be any nonlinear function you want. There's lots of different choices. But we're going to put it after every single hidden layer. We're going to add in this nonlinearity, and it's going to make it so that the space of possible functions that can be represented is very, very different than the linear ones. So we're going to add in this nonlinearity. And the nonlinearity we're going to use is called the ReLU function, ReLU of x. ReLU of x is very simple. It's just x if x is bigger than 0, and it's 0 if x is less than 0. So it just, what it does is you can think of it, if it's a positive number, it goes right through, nothing happens. If it's a negative number, it gets turned into a 0. So it's kind of like an if statement that the network will do. And I made a little spot for this in our code. I said, here is the ReLU function, ReLU. And it's exactly what I said before. Let me implement it correctly.
Excuse me, sir.
Yes?
Sir, why only ReLU means we can use sigmoid or tangent? Or
You can use anything you want. Yeah, that's right.
Okay, it doesn't make any difference.
I mean, it does make a difference, but nobody has a good explanation of when you should use which one and this kind of thing. It's quite complicated to say why one is better than the other. I'll tell you, the nice thing about ReLU is the gradient doesn't go to 0. So if you use tanh or sigmoid, the gradients become 0 for very large numbers, which is harder to learn sometimes. But from a mathematical point of view, any nonlinear function you use will make the space of possible functions you can represent much larger. Which ones work in practice is complicated. Yeah. So we're going to use the ReLU just for funsies because it's simple. And the command is jnp.maximum of x and 0. So it looks at x and 0, and it returns whichever one is bigger. If x is bigger than 0, then it's going to return x. If x is a negative number, then which one is bigger is 0, and it's going to return 0. So very simple function. And all I'm going to do is apply this ReLU function after every jnp dot. So I do jnp dot of wx comma b, and then I'm going to transform the x's. That's going to be ReLU of x. And so what this does is we feed it through the first layer. We feed it through the first layer, and then I do the ReLU of every single die. And then we feed that to the next layer, and so on. So in the next layer, I add in a command that says, don't do w and x, do w and x transformed. So take the nonlinear function applied to the first layer and feed that into the next layer, and then transform it again. Okay, and so transform it again is ReLU of x. In the very last layer, you don't want to do a ReLU. That's because the last layer are logits. We want the logits to be positive or negative. We don't want to turn off the thing. So the last layer is unchanged, but all the intermediate layers, they get this extra little flip of the ReLUs. Okay, so that is that. Let me run it, and let's make sure it's working. Okay, so it worked on some example, and now we batch it, runs on all the things. The loss function, that nothing has changed in the loss function, that's exactly the same. Now we run it. Oh, we got to start the parameters over again. Because we want the parameters to be restarted. Okay, so here we go, it's running. Questions or comments? Over here? Okay, yeah.
For ReLU function, when the x is equal to 0,
Yes.
the point is on differential correct.
That's right, yeah.
Or do we need to have to set a default value for that?
Yeah, the thing is it will never be exactly equal to 0 because it'll be like 0.0001. And so the computer knows, yeah. And actually the differentiation was automatically handled by the JAX package, and it knows about this stuff. So the people at JAX did it for us. Okay, so after one epoch, we're at 85% accuracy. We still haven't crossed 87%. Yeah, after 2 epochs, now we're up to 87%. Let's keep going, and hopefully it'll work. Otherwise, I'm going to be embarrassed. Okay. So let's see. Did I do everything right? Final. While it's running, let me also preemptively check and see if it gets better and better. Be ReLU. Okay, I don't know, let's find out. So we're at 80, 88%. Is it gonna keep improving? Oh, okay, we got better. Let's keep going. And let me see, can I optimize this a bit? Let's put num epochs equals 10. Let's do 10 more and watch it get better. What does it take, like 20 seconds in each one? I wonder if I made the layers big enough. Okay, I have the code that I ran at home that we can use as a backup here, and you have to believe me that it worked, but otherwise we can watch this for a minute or two and see how it goes. It's a good time if there's any questions or comments of adding this thing in. I might not have added enough layers. I added one layer. Maybe I should have added more. Okay, 88, so we've beaten the 87 before.
So what are the parameters that a hidden layer is using?
Yeah, okay, this is a great thing to understand. So let's go over what are the hyperparameters and what are the parameters, right? So the hyperparameters are all the things I set at the beginning. So like the size of each hidden layer, what nonlinearity I'm using, the ReLU, and all of that. The parameters themselves are these little things inside the network. And that is the thing that is being updated. When I do the gradient descent, it's only ever changing the parameters. So in this situation, what are the parameters? They're all these matrix multiplications in the W's. So it's just like when we started, we had the W's and the B's, and now I have W's and B's, but not just one copy, I have one for every single layer. And those are the parameters that are being updated. And they're all baked into the function called, or the variable called params. So params, remember, is like a list, and it has the layers, or the parameters for the first layer, the parameters for the second layer, the parameters for the third layer. In this case, parameters has a matrix, which is 784 by 784, and it has a bias vector of size 784. That's for the first layer. And then it has, in the second layer, it has a 784 by 10, and also a bias vector of size 10. So in this particular example, the number of parameters that I'm actually running on the computer right now is, so on computer now, so it's a 784 of the input. And then I have one hidden layer also of size 784. I could have made this any number I wanted. And then it goes to this 10, which are the logits. So in this layer, there's a 784 by 784 W matrix. And then there's a 784 size bias vector. For this layer, there's a 784 by 10 W and a 10 bias. The second layer is exactly like the logistic regression. This part is the new part. So if you add all this up, 784 times 784 plus 784 plus this, that is the total number of parameters I'm using. And 784 by 784 is like huge. So like most of the parameters are in this first layer. Okay,
So
yeah.
in this particular example, is it like the pixels?
Well, the input is the pixels, right?
Yes.
The stuff going on in this middle layer is just some like abstract numbers that the computer uses as part of finding the output. And so it does, at first it does some operation to go from the pixels to this middle hidden layer. And then the hidden layer gets sent into this layer, and this layer gets sent into the probabilities. But what these represent is like total like abstract stuff. It's like the computer came up with some numbers that help it find the prediction in an uninterpretable way. So I can draw this. This is the softmax. That's what we did already. Those are the layers that we're doing. Does that answer your question? Yeah, I think it's a little mysterious. Like everything you've done so far in this course, it's like everything has a meaning. This one has no meaning. This is like just there for the computer to like, if it wants to write down some numbers as it's going, to use in the next layer. And for some reason this works. And nobody really understands why this works so well. Like it's kind of like, you know, people know that it works, and they know it works really well, and they know you can represent a lot of functions, but it's not like it has a meaning, really. Okay, let's go back and see how our computer's doing. All right, here we go. We hit 90%. Amazing work. If you let it run for even longer, here's one I did at home. This is the one that's in the GitHub. So here I made it even bigger. I said, add in even one more layer. So this one has 784, 784, 784, then 10. And I ran it for a long time, and I got up to 97% accuracy. 97, 97.8, 98, 98, And so this is a much higher accuracy than you can get from the logistic regression. And it's because the space of possible functions that you can represent that are nonlinear is a much bigger space of functions. You can kind of think of this as like we're letting the computer do like a kind of if statement, right? The computer can say if this is not bigger than 0, then do one thing. If it's less than 0, do another thing. And these if statements can combine to get a really good training accuracy. So here it's a training accuracy of 98% and a test accuracy of 97%. This is the other thing that's a kind of a miracle. Very early on in the course, you saw that if you just add more and more parameters, you can like you can overfit the training set and then have a really bad test error. And for some reason, the neural network is not doing that. This is another thing people don't really understand. Why is it that the neural networks don't overfit? Like we added a bajillion parameters. This is something with like some huge, like millions of parameters, and yet it's not overfitting. And that's because the parameters are sort of like coming out one layer at a time, and that somehow helps. We don't really know why. So we know it is not overfitting. We don't know why. But we're up to 98% accuracy with 3 hidden layers. Amazing. The other thing I did is I had it plot some outputs. That's over here. Oh, this one's not going to work. Okay, let's plot some outputs on ours, because that's the one we've been running. Okay, so we only got to 90% accuracy, so still a ways to go. But here's the stuff you can do. So here are the ones. Okay, of course you get them all right? When your accuracy is like 90%, and it's going to always say it's the right label. So here's the fun thing you can do. Find the ones that are incorrectly labeled and plot those ones. So this command goes through all the examples and says which ones did our computer program get wrong, and print those out. Let's see what they look like. And remember, we're getting like 90% right. And the point I want to make to you is that the ones we're getting wrong are stupid. they're like somebody wrote wrong. Like apparently this is a 5, but like whoever wrote this, like clearly like an owl landed on them while they were writing it. And it doesn't look like a 5 to me. So we think it's an 8, it's actually a 5. But I can see why the computer program was confused. This is a great example, right? Our computer program was like, this is a 1. It's like, no, that's a 7. That's a 1, come on. So it's not our fault. Like we're doing fine. Okay, I'll take responsibility for this one. We said it was a 3. It's actually a 2. I'll believe that one. Here are some other weird looking ones, right? This one, our computer said it was a 0. I think it's an 8. Apparently it's actually a 9. So what's the point is that we're actually doing quite well. We're getting most of the examples. If they look kind of sane, then we're getting them. Here's a good example. This is a really slanty 1. Most of the ones in the data set are quite vertical. This one's very slanty. And that's why we mislabeled it as a 3 when it's actually a 1. This apparently is a 5? Hey, this is again. So we're doing quite well. And if we want to improve our performance from like 90% to 100%, you have to start to deal with all these like weird edge cases. And that's what we're getting to by this thing. Okay. Questions or comments about what we've done so far? So what have we done? We started with the most basic thing, which was like linear regression. And just by adding stuff on little by little and doing it explicitly in the code, you can build up to this like really complicated looking thing maybe. But it's complicated, but every individual piece is simple. It's a combination of these individual pieces, and it combines to give something that has much higher accuracy than either linear or logistic regression. This is like the magic of neural networks. Any questions or comments about what we did? Yeah.
So for any problem, how can we decide what number of layers we can keep, and it is possible?
Yes, nobody knows that. Yes. No. So like the question is, can you figure out how many layers you got to do? And the only way is to sort of try it and know. If you do this a lot of times in your career, then you sort of like, oh, this is like that other one, and I did 3 layers for that one, and it worked. So nobody really knows. Nobody has like a great explanation of how many layers you got to do. Setting all the hyperparameters, the number of layers, which nonlinearity, how wide should each layer be, this is kind of like a black art. You just gotta try it and hope that it works. Sometimes it won't work at all. You gotta like fudge things. Yeah.
For the hidden layers, could you make the hidden layers larger than the layers?
You absolutely could. So you can make them larger. The thing is, if you make the hidden layers larger, you're adding more parameters, and when you add more parameters, it makes it slower, right? So at some point, if you make them too big, you're slowing yourself down, and you're not like adding stuff. So as a rule of thumb, people sort of tend to make them smaller as you go, but there's no reason you can't make it really big.
I was asking that because I was trying to think of the edge cases, because if the hidden layers are trying to like form a pattern for like the vertical one,
Right.
Maybe if you make the layers larger.
Yeah. So I mean, you could equally well say let's add more layers. Like that would also try to do that. And so you guys can play with it. You have the code. Feel free to try it. Put in different numbers of layers, different sizes, and see what works well. And you'll find that a lot of the bottleneck is going to be waiting around for it to work. So if you make a really big one with like many layers, you'll run it. It'll take like 5 minutes for every epoch, and you want to run it like 20 epochs, and you're going to be there for 2 hours. The big boys like at OpenAI, they run their thing. It costs them like $20 million to run it because they run it for like a week on like all these like thousands of computers at the same time. So we're doing like the little baby version to learn MNIST. They're doing like, download the internet and like do, predict things. We'll talk a little bit more about those models next week. Yeah, great. Other questions?
Sir,
Yeah.
you mentioned that there are 784 biases in first layer.
That's right. Yeah.
But, previously you told only one bias is there. So
Yeah, there's one bias vector, but the bias vector has 784 components.
for each neuron, like
Yeah, so for each neuron it's one number,
Oh.
but there's 784 numbers. So this count over here is the number of numbers that the computer has to memorize, right? And that's relevant. Like a number takes up like some number of bits in the computer's
for
storage.
each neuron is bias.
That's right. So a bias, you should think of it's a bias vector and a weight matrix. A weight matrix is some like box collection of numbers, and a bias vector is some list of numbers. That's another thing. If you try to make it too big, the computer will yell at you and say out of memory. So eventually you're going to run out of memory either on the Colab instance or even on your home computer. You can only store so much. And this is like the really big models like they use for ChatGPT usually are too big to fit on one computer. So you can only fit on like a really big computer or like multiple computers like linked together. So this is like one of the bottlenecks is like running out of memory to store all your parameters.
Would there also be a point where the many layers don't really need to be?
Yes, that's totally true. So yeah, or if you make them too big or like you add more layers, you can saturate. I believe for MNIST, like the data set we're doing on, people have gotten it to above human performance. So the neural network does better than a human. I think a human only gets like 98 or 99% accuracy on this data set, again, because of these like silly ones like this, right? So like humans get this one wrong all the time. Okay, apparently that's a 5. So the neural networks are at the point, this data set is like very well understood, and like you can write a model just like we did that will beat humans and it'll train very quickly. But yeah, on harder data sets, it's a different story. Okay, let's stop there. Next class, we're going to do more neural network stuff. They're going to get more complicated. I'm going to show you like other cool things you can do, and then we'll learn a little bit about like language models and how they work and that kind of thing. Okay, see you guys on Monday. Don't forget to do your reviews and post any suggestions you have for the final project.
So it does what we